This is the Algebra 2017 paper, just going through it to double check some of the information following some queries from students. So, looking at this first one, we've got an x, so it's going to be linear. We've got minus 0.5, so it's going to be negative. For equation 2, we've got e, so it's going to be exponential. For equation 3, we've got an x squared term, so it's going to be quadratic. Equation 4, we've got a something over x squared, so it's going to be looking a bit like that. We've got a square root graph, which is the inverse of a quadratic, so will look like that. And we've got a log equation, which is the inverse of an exponential, so should look like that. So, looking at our data sheet, we have a negative linear graph is G. Equation 2, our exponential graph, is going to be B. Our quadratic graph is D. The x squared over x squared will be C. The square root graph will be A, and the log one will be F. Question 2, so we have 2ai to start with. Maximum loudness, we are told on the data sheet, is our amplitude, so that is 45. The frequency of the note, we are told the frequency is 360 times the frequency gives you the big number, so we should have 237,600 over 360, so we've got a frequency of 660. Okay, so given that it's a 2-mark question, realistically we also need to have our working out. And that equals F. So, part B, we are starting to look at transformations. So we need the graph that maps sine t onto 45 sine t, so that will be a stretch parallel to the y-axis, scale factor times by 45. And then secondly, we have a different graph, and so both of those have got the 45 in common. The translation is going to be the other bit, so we are translating this section here, so that will be a stretch parallel to x-axis, scale factor times by 1 over 237,600. Part C. So we've been asked to, for this equation, complete the table on page 6 answers to 2 decimal places. So if we go into a table, and then we want to set up our table, and our table, if we start it from the beginning, 2, 2, 2, and we go up to 0.0036, then at least we are in the position, and we are going up in 0.0002s, because at least that way we can double check that our first couple are right. So 2 decimal places, yes, 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 yes. So our next one will be where are we? There. So next one will be 1.3, 2 decimal places, so rounding, 1.78 with rounding, 1.41 with rounding, 0.50, and minus 0.86. So that gives us everything to 2 decimal places. We're next asked to draw the rest of the graph, so the section that's missing. So that'll be a case of plotting the points we've got. If you look on your calculator, then you can see that your graph should look a lot like this, which gives us a better idea of roughly where we are. So 0.002, each of the little ones is going to be worth an extra 1, so that's fine. And on the big squares, each big square is worth 1, so each little square is going to be 0.2. So that's going to be at minus 1.68, which is nearest damn it 1.7. So we should be in there. Then we've got one little square, sorry, 2 little squares up, we've got 1.32, and then minus 0.5, which is there, then plus 0.5, which is there. And as you can see, we've got the right curve for what we're expecting coming out. So 1.32 is going to be there. Then at 3, then 1.41, um, 0.5, and then minus 0.86, which is going to be minus 0.86. So we've got the pattern that we're expecting, and they are going to want a smooth curve. It's worth just double checking. So G-solve maximum, got our first maximum, our second maximum, Okay. So we've got our first maximum. No. Calculator's dead. Oh no, just slow. It's worth double checking your maximum and your minimum and then drawing a nice smooth curve in pencil. So that will come down, follow through your dots, and then is going to meet up beautifully. You obviously aren't allowed any weird kinks, double lines, that kind of thing. So if you've got a bit that's a bit wobbly, we're going to have to wire a bit out and stop. Okay, so Patrick believes that the profit, which is y, is this equation and x is the unit price. So if Patrick is selling shoes at this, it's going to be a loss, which means we're expecting a profit. So y has got to be less than 0. So for 3a, we have y equals minus 2 brackets 145 brackets squared plus 324 brackets 145 brackets minus 7082. This can go onto any type of calculator. It's not going to be a problem either way. Squared plus 4 is 145. So we've shown that we've substituted in. We've got our numbers out, and it's coming out at y equals minus 2152. So makes a loss of £2152. We have then been asked to express it in this form. This is the completed square form, so we are going to need to find the maximum. In order to write it in this form, we're going to need to find the maximum point. So G solve max. So we know that at the maximum point, y is 6040 and x is at 81. So this is going to look like y equals minus 2 brackets x minus the x coordinate at the maximum squared plus the y coordinate at your maximum. Okay, so very helpfully it then kind of tells us what we've got to have done, just in case we've forgotten. So our maximum unit price was 81, maximum profit was 6040. So for part D, if Patrick makes £5,000 profit, we want possible values, and values has an S on the end, and we want it in pounds nearest penny. So if we substitute that into our equation, we can write that as 5,000 minus x squared plus 324 x minus 7082. And then if we go G solve, and we want to know what x is when y equals 5,000, and there will be two values. So x equals our first value is £58, and we want it to the nearest penny, which is 20p. And moving across to our second value is £103, 80p. Right, question 4. So, we are told what E is, we are told what A is, we are told that we have a length of 6 meters, and we have a point load of W kilonewtons. We have a maximum possible deflection, and we want to know what the maximum value of of omega W is. So we need to use this first equation. So we have, for 4 part A, we have y equals omega L cubed over 48EA. So substituting in, we know that the maximum possible deflection is in millimeters, and it is normally measured in meters. So y is going to be, so y is going to be 24 divided by 10 to turn it into centimetres, divided by 100 to turn it into millimetres. Sorry, to turn it into metres. So we have 0.024, and that's in metres. And the others are units that we'd hope for. So we know that 0.024 is equal to omega times L is 6 meters, and that is divided by 48 times 2.2 times 10 to the 8 times 4.2 times 10 to the minus 10. No, times 10 to the minus 4. So what we're going to have to do is we will times this by this mass and then divide by 6. So we should get omega equals 0.024, and then as we bring this across, we've got times by 48 times by 22.2 times 10 to the 8 times 4.2 10 to the minus 4. So 6 omega is going to be 53224 over 5. Then if we divide that by 6, then what we've got is 1770.8 or 177, and that's in 177,000, and that's in kilonewtons at the midpoint. You can also do that by replacing the W with X, and then using xcal on your calculator, where Y is 0.024. We have another steel beam, only this time our steel beam has a length of 8.5. It is a uniformly distributed load, so it's the other equation, 16 kilonewtons, maximum deflection. So, if we are doing a uniform load, then that is this equation. So for part B, we have y equals 5w L cubed over 384 A. We know that L is 8.5. We know that omega is this per meter. So we know that omega is 16 times 8.5, and E and A are as they were before. So Y is going to equal 5 times 16 times 8.5 times 8.5 cubed over 384 times E, and E was 2.2 times 10 to the 4, 0.2 times 10 to the 8, and then that is times by 4.2 times 10 to the power of minus 4. Hopefully we should get that, and that is in meters. So we're going to need to write down what we typed in. So we had 5 times W, which was that, times 8.5 times 8.5 cubed, all over 384 times 2.2 times 10 to the 8 times 4.2 times 10 to the minus 4, and that gives us 0.0117696244, and we want the maximum deflection, so that is going to be equal to 0.0118 meters, or if we times that by 100, that will give us centimeters, or if we press it twice, then that's not going to help. So that is 11.8 millimeters. Don't need this bit. Probably wouldn't put it in. Okay, so part C. We have another uniform load that is in per meter, maximum possible deflection, and we need the span length. So we know that Y is going to be 20 millimeters, and that is the same as 2 centimeters, and that is the same as 0.02 meters. So 0.02 meters times 5, because it's a uniformly distributed load, times 14, which is the force per meter, times L, which is the number of metres, times L cubed. And that will all be divided by 384 times 2.2 times 10 to the 8 times 4.2 times 10 to the minus 4, because that's the E and the A that we're working with. So we need to find out what L to the power of 4 is. So on top we've got 5 times 14, so we've got 70 L to the 4, and on the bottom we have 384 times 2.2 times 10 to the 8 times 4.2 times 10 to the minus 4. So that's divided by 5481600, and that's equal to 0.02. So if we rearrange that, we end up with 0.02 times crazy big number divided by 70, and that equals L to the 4. So that times 0.02 divided by 70. So we know that L to the 4 equals 10137.6. And so we need to find out what just L is. So we can put that to the power of a quarter and we should come in at L is 10.0 meters.